Tonight's webinar is on the subject of spark plugs, and I have to warn you guys, this is the first time I've done this. This is not a talk that I've done at AirVenture before or anything, so you're all beta testers. But it's an interesting subject, and we've got a lot to discuss. I'm going to start out going through some of the basics of aircraft spark plugs, electrode designs, barrel designs, heat ratings, all that kind of thing. Talk a little bit about preventive maintenance of spark plugs and when it's time to retire them and replace them. And then at the end, I'm going to get into some fairly new issues that we've been seeing with spark plugs in recent years. Problems with high resistance, problems with nose core insulators cracking, and bring you up to speed on some of that. Talk a little bit about the two brands of of certificated spark plugs that are available, Champion and Tempest, and discuss a little bit about how the two brands differ and what the pros and cons are. So with that, let me get started. And I thought a good place to start would be to talk about the part numbers of spark plugs, because it sort of gives us a chance to review a bunch of different characteristics that we're going to talk about individually. So here's a typical spark plug number. It's actually the UH or V32E is actually the spark plugs that I use in my own airplane. And let's just go through and decipher the number. The U prefix indicates that the plug is made by Tempest. If it was just an RHB32E, it would be a Champion spark plug. And nowadays we have two companies that are making spark plugs for certificated engines, Champion and Tempest. Tempest acquired the Autolite spark plug line from Unison, and the U prefix actually originally stood for Unison, but now Tempest owns it. But to keep things simple, they left the part numbering the same. So if the part number starts with a U, it's a Tempest plug, and if it doesn't start with a U, then it's a Champion plug. The next thing is an R, which means it's a resistor plug, and virtually all of the plugs that are used these days in certificated aircraft engines are resistor plugs. We'll talk a little later about what the resistor is there for and some problems that we've been seeing with the resistor, but literally all of the spark plugs that are used in certificated aircraft engines now have the R. They start either with an R or a UR, depending on who manufactures the plugs. The next letter indicates the barrel style of the plug. There are three different styles. The barrel style means the part of the plug that hooks to the ignition lead, as opposed to the business end of the plug. And there are basically two different styles that are used in the U.S. The standard style that is designated with an E, and the all-weather style, which is designated with an H. Most piston aircraft engines can use either the E or the H plugs, but they have a different size and pitch of thread where the harness hooks up. So which kind of plug you use depends on which kind of harness you have installed. And if you wanted to change from standard plugs to all-weather plugs, you would have to replace the ignition harness so that the ignition harness connection at the plug end was compatible. And we'll see pictures of both of those. The next letter, the B in this case, defines the business end of the plug, if you will, the end that screws into the cylinder. And it tells you what the thread size is. Most modern aircraft, certificated aircraft engines have 18mm plugs, although there are some that still use 14mm plugs. Small. That 14mm is pretty much the size that most automobile plugs are, but aircraft plugs are typically 18mm plugs. That's the diameter of the threaded boss in the cylinder head that you screw the plug into. The plugs can be either long reach or short reach, depending on the particular cylinder head involved. For normal 18mm plugs, a long reach plug has a reach that is the length of the threaded portion that's 13/16 of an inch. It's called a long reach plug. Or it may have a short reach that's a 1/2 inch long. Again, I'll have a picture of that for you. And in both cases, the hex size on the plug, that is the size of the socket that you need to torque the plug into place, is 7/8 of an inch. The next part of the part number is a 2-digit number that represents the heat rating of the plug. Again, we'll talk about exactly what that means in a moment. But basically, there are a variety of heat ratings. The lower the number, the colder the plug, the hotter the number. I mean, the higher the number, the hotter the plug. And the most common heat ratings used nowadays in certificated aircraft engines are shown there: 32, 36, 37, 38, and 40. With 32 being a cold plug that's used in a high performance or high compression engine, and a 40 being a hot plug that's used in a low performance, low compression engine. We'll talk a little bit more about that in a moment. And then finally, the suffix, the last letter, which is an E in this case, discusses the design of the electrode. And there are a number of different designs, but nowadays there are basically 3 of them that are in common use. E represents a normal massive electrode plug with 2 large nickel ground electrodes. That's the most common kind of plug that's in use, and that's the sort that I use in my own airplane. S plugs are fine wire plugs made with a single iridium ground electrode. The fine wire plugs are much more exotic. They're much more expensive. They last longer, and there are some advantages of fine wire plugs that we'll talk about. And finally, there's a kind of an oddball plug that is used in small Lycomings 235s called a BY plug that has kind of a unique design that was created because those small Lycomings tend to have a lot of lead fouling problems, and yet most people don't want to spend $100 a spark plug to put fine wire plugs in those little engines that are typically used in trainers and low performance aircraft. So they came up with a peculiar massive electrode plug called a projected core nose plug. It has 2 nickel electrodes, but they're configured differently in a way that's more resistant to fouling. It's only available in the 37 heat range, and it's normally only used in itty-bitty Lycomings. 235s, I think, is primarily what they're used for. So there are lots of different possibilities. If you look in the Champion or the Tempest catalog, you'll see that there are a lot of different spark plugs available. The most common ones that we see most often are shown in that little red box in the lower left of the slide. But at any rate, that's how these part numbers are deciphered. And let's go ahead and talk about some of these specific characteristics. Starting with electrode design. As I indicated, there are basically 3 electrode designs that are commonly used today. The most common is a massive electrode that's designated by an E suffix with a big round center conductor and 2 big thick nickel electrodes, as shown in the left-hand photograph. By far, that's the most commonly used kind of spark plug, and it happens to be what I have always used in my own airplane. They're relatively inexpensive. They tend to last 400 or 500 hours before they get worn out. Well, I'll show you how we determine when they're worn out, and then you replace them. And they're, $20 spark plugs roughly. The one in the middle is the fine wire plug, which is has a single iridium precious metal electrode, and it's designated with an S suffix. These plugs are 3 or 4 times as expensive as the massives. They last 3 or 4 times as long, so on an hourly life cycle basis, the cost is roughly the same, as long as the plug isn't damaged or either by you or your mechanic or by operation. And I'll be talking towards the end of this webinar about some of the problems we've been seeing with fine wire plugs meeting their demise before their time. But in any case, that's what the S-type plug looks like. It's got very expensive and exotic materials for its electrodes, and they wear a lot longer, but they cost a whole lot more. And then the right-hand picture shows that funny BY plug I was talking about that's used in small Lycomings. It's a massive electrode plug, but it has a projected nose core design that makes it more resistant to lead fouling. And it's used in the small Lycomings because they're particularly prone to fouling. They were designed for 80-octane fuel. And when 80-octane went away and we had to start running on 100 low lead, it turned out that these engines had really terrible fouling problems, and so this BY plug was designed specifically for those engines. I mentioned earlier that plugs can be either long reach or short reach. The reach refers to the length of the threaded area that screws into the cylinder head. It's absolutely crucial that the plug that you use the correct reach plug, because the correct reach plug, when it's screwed into the cylinder head with a copper gasket under it, is such that the end of the thread winds up being basically flush with the inside of the combustion chamber, which is what we need. And if you put a short reach plug into a cylinder head that needs a long reach one, you're going to have a really awful ignition. But if you do the opposite, put a long reach plug into a head that needs a short reach plug, then the end of the plug will project into the cylinder head, and that could be a real catastrophic error. So we need to make real sure that we're putting the correct reach length plug into the cylinder head. Next, let's talk about heat ratings. As I mentioned, these plugs are available in a variety of heat ratings. Most commonly nowadays, the heat ratings range from 32 to 40, 32 being a colder plug, 40 being a hotter plug. And what does that mean? Well, what it means is the difference between a cold plug and a hot plug has to do with how rapidly the nose core of the plug dissipates heat. That's controlled by how long that nose core is from the tip of it to where it's attached to the plug barrel and gets to shed its heat into the plug barrel and then ultimately into the cylinder head. The longer the heat transfer path, the hotter the plug will run, and the shorter the heat transfer path, the cooler it will run. The idea here is that some engines run very high combustion temperatures and some run lower combustion temperatures. And for an engine that runs high combustion temperatures, typically high compression or turbocharged engines, we want to use a colder plug that dissipates that heat more readily. And for engines that have low combustion temperatures, because they're low compression engines or low performance engines, we want a hotter plug so that the core insulator remains hot enough that we don't get a bunch of carbon and lead deposits and stuff on it. So where the heat rating of the plug is sort of trying to compensate for the combustion heat of the particular engine involved. And we need to get it in a sweet spot. We want the nose core insulator ideally to be running right around 1,000 to 1,300 degrees Fahrenheit. If it's much cooler than that, then it will start to develop carbon deposits. And if it's below about 800 degrees Fahrenheit, the lead scavenging agent in the fuel, the ethylene dibromide that's blended in with avgas, will not be able to properly do its job of lead scavenging, and you'll start to get buildup of metallic lead in the spark plug. So we want to make sure that the plug is running hot enough to prevent lead and carbon buildup. But if it runs too hot, then it can actually start to ignite the fuel-air mixture prematurely before it's kind of like a glow plug, and create really awful things, destructive pre-ignition, which can actually destroy a cylinder. So we have to keep the spark plug nose core temperature in a sweet spot, and we do that by using a heat range that's appropriate to the particular engine involved. High compression and turbocharged engines generally need a cooler plug to protect against pre-ignition. Low compression engines, particularly ones that were originally designed to run on 80-octane fuel, which of course we can't get anymore, generally need a hotter plug to protect against lead fouling and carbon fouling. I mentioned earlier that there were two different barrel designs commonly in use: the standard one that has a 5/8 inch thread, and the all-weather design that has a 3/4 inch thread. The two different plug designs mate with two different kinds of connectors at the end of the ignition harness, and you can see that there's a difference in diameter. If you need a 7/8 inch wrench to remove what's called the B-nut to disconnect the harness from the plug, then you have an all-weather plug. If you use a 5/8 inch wrench, then you have a standard plug. The all-weather plugs have some advantages. They were designed to provide improved sealing against moisture. And if you fly the airplane particularly in a lot of actual IFR or in the rain and that sort of thing, it would probably behoove you to install all-weather plugs. But again, you can't just switch from standard plugs to all-weather plugs without also changing the ignition harness. When you order an ignition harness, you have to specify both what kind of maggot it hooks up to and which kind of plugs, standard or all-weather, it hooks up to, because the connectors are different. But in any case, again, if you fly a lot of IFR, fly in precipitation, that sort of stuff, it's probably worth converting to all-weather plugs because it keeps moisture out of the plugs. Let's talk a little bit about electrode wear. In the top two photographs are showing a standard massive electrode plug. The lower one are showing iridium fine wire plugs. And in both cases, as you can see, as the plug remains in service, metal erodes from either the center electrode or the ground electrode, depending on which polarity the plug is firing. And the electrodes, in the case of the ground electrode, just gets thinner and thinner. In the case of the center electrode, if it's a massive plug, the center electrode starts with a cross-section that looks like a circle, and it gradually wears to a cross-section that looks like a football. And also the thickness of the ground electrodes gradually get thinner and thinner over time. The basic rule is, and this works for both fine wire plugs and massive plugs, that the plug should be considered to be worn out and should be retired and replaced with a new plug when either the center electrode or the ground electrode reaches half of its original dimension. In the case of the center electrode on a massive plug, half the dimension means that the center electrode gets football shaped to the point where the short diameter is half the long diameter. And in the case of the ground electrodes, it simply means that the electrodes get have half as much meat on them, if you will, as they started out with. The same thing is true of the fine wire plugs. They wear much more slowly, and of course, there's the electrodes are much smaller in diameter, or smaller in thickness, but they kind of wear the same way. The ground electrode gradually gets thinner, and the center electrode gradually gets not football shaped in this case because there's only one electrode, but sort of flattened on the side of the ground electrode because it's losing metal every time the spark fires. For massive electrode plugs, the kind that are most commonly used, their Champion makes a little go-no-go gauge that you can use rather than trying to estimate when the electrodes are half the original size. The way this little thing works is just a little hunk of metal with a calibrated beveled hole drilled in it. And the way it works is you clean and gap the plug to its normal gap, which is 16 thousandths of an inch. And then the last thing you do is you stick the nose of the plug into the hole. And if it goes through the hole, then the plug is considered to be worn out, and you throw it out. And if it can't go through the hole, then it can remain in service. You don't have to use this gauge. It's just a convenient way of doing the go-no-go test. And there is no similar gauge for fine wires. That one you have to do by eyeball. We need to clean these plugs periodically. Usually every 100 hours is a good rule of thumb. I have taken to start cleaning my plugs on condition rather than on a fixed timetable. I do in-flight lean of peak mag checks every few flights, and when the plugs start to get contaminated, I can start to see that the engine starts running a little bit rough, and the EGTs start getting a little bit unstable when I'm doing a lean of peak mag check and running on just one mag at a time. And at that point, I decide it's time to clean the plugs. But most people do it on a fixed timetable, and typically 100 hours of operation between cleanings is about right. So, you know, if you fly 100 hours a year, you can do it at the annual inspection. If you fly significantly more than 100 hours a year, you probably will need to clean your plugs more than once a year. If you want to do this yourself, there's inexpensive equipment available to do it. That thing in that bluish thing in the upper left-hand corner is a sandblaster for spark plugs, and the little thing that looks like a Dremel tool is a vibrator. Basically, cleaning the plug involves two steps. The first thing you do is use some sort of a vibrator that dislodges any accumulated metallic lead deposits that have jammed themselves into the plug. And once you've used the vibrator to get the lead removed, then you sandblast the plug with pressurized air and an abrasive compound to clean the thing up. And you can buy these things very inexpensively. If you do a lot of spark plugs, if you're running a shop or something, then there are some quite elaborate and expensive tools for spark plug cleaning that are shown down at the bottom. But for example, that whitish unit there, which actually is both a spark plug cleaner and a spark plug tester, is about a $500 unit. So it's the kind of thing that you might buy if you're running a shop, but it's probably not the kind of thing that an individual aircraft owner who's doing preventive maintenance would want to invest in. Those things up near the top are more within an aircraft owner's budget. They're, you know, $20 or $30 kind of things. But in any case, that's what's involved in cleaning. There's actually one other option which I adopted quite some time ago. There's a company in Van Nuys, California called Aircraft Spark Plug Service, And I fly a twin that has 24 spark plugs, and cleaning 24 spark plugs is a lot of work. So typically, when I down the airplane for a week or so, I'll just pull the spark plugs out, send them to aircraft spark plug service. They normally turn them around in a day or two and send them back all nice and cleaned and gapped and tested and packaged in sealed plastic bags. And I think I believe they charge $3.50 a plug. I figure I can't clean them for $3.50, so I figure it's a pretty good deal to send them off to aircraft spark plug service. If you're interested, just Google aircraft spark plug service, and you get all the details. But it's a real good company, and I've used them for years. We need to the spark plug gap erodes as the spark plug remains in service, and so periodically it has to be readjusted. Most of the plugs used in certificated aircraft specify a gap of 16 thousandths of an inch, 0.016, and the gaps need to be measured with a wire gauge like that red thing that you see on the slide. You can't use a flat type thickness gauge. That won't work in a spark plug. You have to use a wire. And so normally to check the gap on a plug, on the right side of that thing there are two little wires sticking out. One is 0.019 and one is 0.015. The 015 ought to pass through and the 019 shouldn't, and if that's the case, then the plug is gapped properly. The gap widens in service, and so normally at each 100-hour service you need to readjust the gap back to 0.016, and the way you do that is to use a little mechanical squeezer to squeeze the ground electrodes a little bit closer. You have to do it really carefully, because if you overdo it and get the gap too small, you have to throw the plug out. You can't open up a gap once you've made it too small. To squeeze the gap down, you can get a real fancy gapping tool from Champion that clamps to your workbench, that thing over on the very right side, but it's pretty expensive. If you just do, a handful of plugs, you can use a real cheap little tool like the one down near the bottom, just to the right of the gapping gauge. If you use fine wire plugs, there's a special tool, that thing that's marked CT457, that's used for bending the fine wire ground electrode. You want to be really, really careful doing that, because the iridium electrodes are extremely brittle, and they get more brittle as the plug remains in service, and it's really, really easy to break them off when you're trying to adjust the gap, and you just wound up trashing a $100 spark plug. So we don't really want to adjust the gaps on fine wire plugs unless they really need to be adjusted, and then we want to do it very, very carefully, and it uses that little special tool. Now the spark plug gap is very critical, so it's very important that we keep it right within the standard tolerance. The gap is supposed to be 0.16. The maximum allowable gap is 0.21. I don't like to see the gaps get up anywhere near that high, so I regap my spark plugs on a pretty regular basis. If the gap is too small, then the spark that the plug throws is weak, and you won't get a real good ignition. If the gap is too large, then it takes a lot of voltage to fire the plug, and when the engine is turning at low RPMs, and particularly when you're starting the engine, the magneto is not putting out as much voltage as it would when the engine is running at normal in-flight RPMs. And so if the gap is too large, you may have a hard time getting the engine started. So we want it to be just about right at what the spec says, which for most plugs is 16 thousandths. And again, either regap them every 100 hours, or if you want to do it on condition, do regular in-flight lean and peak mag checks, and when you start to see the performance erode, it's time to clean and gap them. Then installing the plugs, I won't go through the details, but you need a bunch of tools to do that if you're doing the stuff yourself. Having a spark plug tray to keep the plugs organized is extremely convenient. It makes it a lot easier not to drop them or let them roll off the bench and get ruined and stuff. You need a special 6-point deep spark plug socket designed specifically for spark plugs. If you use a standard 12-point socket, it will tend to wreck the hex on the spark plug, and you'll have to throw the plug out. Some people use a special open lead wrench, like that T-handle thing that I've shown, to attach the spark plug leads. They can be handy. I don't actually use a wrench like that myself, but a lot of people do. Obviously, you'll need a good torque wrench. Spark plugs always have to be installed with a torque wrench. For reasons that I've never totally been able to understand, the torque spec from Lycoming and Continental are different. I don't understand why that is, because the plugs are the same and the gaskets are the same. But Lycoming specifies 30 to 35 foot-pounds. Continental specifies 25 to 30 foot-pounds. So if you want to just remember one number, remember 30 foot-pounds or 360 inch-pounds. That works for both Lycomings and Continentals. Most people, when they're attaching the B-nut on the ignition lead to the spark plug, will do it by feel. After many years of doing it by feel and discovering that that's not a really reliable method, I started years ago to actually use a torque wrench to tighten the B-nut as well. If you tighten the B-nut too tight, it's just about impossible to get the ignition lead off. It's a very common rookie mechanic mistake, and if you don't tighten enough, of course, it can vibrate off. So I tighten my B-nuts to 10 foot-pounds or 120 inch-pounds, and that seems to be very, very reliable, and I've never had a B-nut problem since I started using a torque wrench. Anytime you install a spark plug, you should install it with a new copper spark plug gasket. They're about 10 cents a piece. You buy them in boxes of 100, and that'll last you pretty much for the rest of your life. But you never want to reuse a spark plug gasket, because the gaskets work harden, and if you try to reuse them, then the spark plug won't, the gasket won't seal well, and you run the risk of the spark plug backing out, and that can cause very horrible things. Also, when you install a spark plug, you normally apply a special liquid anti-seize to the threads. That bottle that you see in the picture is the Champion product. Tempest also offers a similar product. I think they're probably identical. It's a liquid anti-seize that has a lot of carbon in it to make it very conductive, to provide a really good electrical path from the spark plug, the threads on the spark plug, into the cylinder head. You need to be really careful not to apply too much, because if the anti-seize drips onto the electrodes of the plug, it'll short out the plug. So we use just a little drop on each plug before we install it, and you try never to get any anti-seize on the very last thread, just to make sure that it won't leak and contaminate the business end of the plug. We'll talk a little bit about firing polarity. Turns out, we talked about the fact that metal gets eroded from the spark plug electrodes every time the plug fires. That's why they gradually wear out. And it turns out that if the spark plug is fired with a positive voltage, the ground electrode is the one that loses metal. And if the spark plug is fired with a negative voltage, it's the center electrode that loses metal. This is the same on massive plugs. I just used this picture of fine wire electrodes just because it's easier to see. Now, in radial engines with odd numbers of cylinders, the spark plugs fire with opposite polarity on alternate firings, so the wear automatically balances out. But on flat engines that have an even number of cylinders, it turns out that each spark plug always fires with the same polarity. Half of the plugs fire with positive polarity and the other half of the plugs fire with negative polarity. So if you leave the same spark plug in the same position throughout its life, literally all the wear will be either on the ground electrode or the center electrode, and the plug won't last nearly as long as it would, say, in a radial engine. So the solution to that is that whenever we remove the spark plugs for cleaning and gapping, we don't reinstall them in the same position, but we rotate them to equalize the wear. And this diagram shows the recommended rotation pattern for both 4-cylinder and 6-cylinder engines. The main thing is that we want to rotate the plugs, first of all, so that they always move from a positive position to a negative position. And second of all, bottom plugs live a much worse life than top plugs, because they're kind of the drain plug for the cylinder, and they get oil and they get lead and they get carbon and other garbage into them. So while we're rotating the plugs, it's also a very good idea to rotate them in a way where the top plugs go to the bottom and the bottom plugs go to the top, so that each plug spends half its life in the bottom position, which is very tough on the plugs, and half its life in the top position, which is much easier on the plugs. And so these recommended rotation patterns accomplish both of those things. They alternate the plugs from positive to negative positions, and they alternate the plugs between top and bottom. And by doing this every 100 hours, when the plugs come out anyway for preventive maintenance, you'll get significantly longer life out of the plugs than you would if you weren't rotating. Whenever the plugs come out, typically every 100 hours, they're always inspected to see what condition they're in. Here are some different things that we would look for during a spark plug inspection. And of course, the big thing we're looking for is how worn the electrodes are and whether the plug needs to be retired or whether it can remain in service. But we're also interested in whether it's oil fouled or lead fouled or that sort of thing, carbon fouled, because it will tell us about what's going on in the cylinder. If one plug is carbon fouled, it probably means that, especially the bottom one, it probably means that cylinder has got some oil burning issues and so on. So it helps us. It's one tool we have for understanding what's going on inside the cylinders when we inspect the spark plugs. Plug fouling is a significant problem, more so with some engines than others. Typically, the lower performance and lower compression engines have more problems with fouling than the higher performance ones, but we see this problem in all sorts of aircraft, including high performance and turbocharged airplanes. Most of the fouling occurs during low power operation, particularly when you're on the ground, because the core insulator, the spark plug, is just not getting hot enough during ground operations to allow lead to be scavenged, and so it starts building up on the plugs. Obviously, the way to reduce that, a couple of things. One is to not do excessive ground operations any more than you have to. Another is to lean very aggressively during all ground operations. If you have viewed my webinar on leaning, or if you want to, of course, it's online on the EAA video server. I talk quite a bit about how we should be leaning very, very aggressively during ground operations. But engines should be leaned brutally during ground operations, and by that I mean leaned as far as they can be without the engine actually stumbling. We want to get the temperatures, the combustion temperatures during ground operations up just as high as we can in order to keep the spark plugs clean, and a couple other things like keeping the exhaust valve stems clean, so on. Other ways to reduce fouling: fine wear plugs are much less vulnerable to fouling by their design. So if you have serious fouling problems that you can't eliminate any other way, you may want to consider using fine wire plugs. Some people, because fouling mostly occurs in the bottom spark plug, some people actually will put fine wire plugs in the bottoms and massive plugs in the top just to save some money, but to get the fouling resistance of fine wires. I've never found a need to use fine wire plugs if the engines are lean correctly, but it varies from engine to engine and aircraft to aircraft. Fouling can be reduced by using a hotter heat range spark plug, but the problem is, of course, going to a hotter heat range spark plug will also increase your risk of pre-ignition damage during high power operations. So the manufacturers specify a specific number of different heat ranges that are allowable for an engine, and you shouldn't ever go outside of that range, either on the top or the bottom. But if you have multiple heat ranges that are authorized for your engine, using a hotter plug will reduce fouling. And finally, in extreme cases, you can add TCP, tricresyl phosphate, to the fuel. Alcor packages it or sells it in quart containers, and you add a little TCP every time you top off the tank, and that provides some additional chemical lead scavenging, and that can sometimes help in extreme cases of lead fouling. Okay, let me shift to two significant problems that we've been seeing with spark plugs lately, and that are not widely understood, which is why I want to spend some time about them in this webinar. And I'll start with the problem of spark plug resistors. Almost all of the spark plugs that we use nowadays in certificated aircraft have a resistor built in to the plug. That cutaway diagram at the right shows the resistor inside the plug. And the purpose of the resistor is to limit the current flow across the plug electrodes when the plug fires. If there were no resistor in there, then there would be a higher current flow through the plug, and more metal would be transferred from the electrodes, either the center or the ground, depending on polarity, when the plug fires. And so to increase the life of the plug, the manufacturers install a resistor in there that limits the amount of current that flows through the plug when the mag fires. Normally that resistor should be about 1,500 ohms, somewhere between 1,000 and 2,000. 1,500 seems to be about the standard value in a brand new spark plug. And that resistance value is moderately critical. If the resistance was too low, then the plugs would fire with a high current, and the electrodes would wear rapidly. That's the reason the resistor is there, to limit the wear rate of the electrodes. On the other hand, if the resistance is too high, then there is reduced current flow through the plug, and the plug will fire a weak spark. And if the resistance gets high enough, it can cause collateral damage to other parts of the ignition system, like magnetos or ignition harnesses, because if the resistance is high enough, then when the mag fires, the electricity may find another path with lesser resistance. Either if the plug itself is too hard to fire, then the spark may penetrate through the insulation of the spark plug lead and compromise the lead, or it may crossfire inside of the magneto distributor cap and compromise the magneto. We have specifically seen numerous cases of aircraft that use slick mags, which are physically the smallest of the mags available, and so are most vulnerable to crossfiring inside the mag. And we've seen a number of cases where spark plugs that have very high resistance values can actually destroy a slick mag, and I've personally seen that happen, half a dozen times or so. But for example, in the Cirrus SR20s that my company manages, which the early SR20s were delivered with slick mags, and the later ones used Bendix mags, which are less vulnerable to this problem because they're physically larger, and so there's less potential for internal crossfiring in the mag. But the point being that if the resistance is way too high, there can actually be collateral damage in other parts of the ignition system, so it's not a good thing. Now, for that reason, we've started recommending that whenever the plugs are out of the airplane for maintenance, that they should be measured with an ohm meter to find out what the resistance is. And you can use a conventional ohm meter, and you set it to ohm, stick one probe into the contact well and the other probe touching the center electrode, and measure across the resistor. And again, the normal resistance should be somewhere in the 1 to 2,000 ohm range. And we recommend that if the resistance gets above 5,000 ohms, then the plug should be discarded, even if the electrodes still look fine, because as the resistance starts rising, the intensity of the spark decreases, and if it rises enough, it can actually start taking out harness leads and magnetos and stuff. Now here's the thing I want you to be aware of. We have been seeing an epidemic of high resistance problems in Champion spark plugs over the past 3 or 4 years. It's probably been going on longer than that. It's just that normally nobody measures the resistance of spark plugs, and so people haven't been aware of this. But when we started doing that, we've started seeing that the resistance of Champion spark plugs after they've been in service for a while can be way out of whack. These photos that you see show 3 different Champion spark plugs that were 3 years old, had 450 hours on them, and as you can see, one measured 35,000 ohms, which is about 25 times too great. Another one measured 200,000 ohms, and the last one measured 1,000,000 ohms. Totally way out of whack. Now, we've not seen this problem in Tempest plugs, and the lower photograph shows a Tempest plug that was measured again after 3 years and 450 hours in service, and it measured 1,500 ohms, 1,500 ohms, the same as it was when it's new. And to be honest with you, I've never ever seen a Tempest plug have a bad resistor, but we see it all the time in Champion plugs. The reason for that is that there's a significant difference in the design of the plugs. By the way, before I get to that, here's another example. This is a tray of 12 fine wire Champions that came out of a Cirrus SR22 turbo, and that was measured, and those 2 pictures show the front and the back of the spark plug tray where the mechanic noted down the resistance measurements. Only 1 out of the 12 spark plugs measured less than 5,000 ohms, measured 3.3 thousand. All of the others were over 10,000 ohms. Almost half of them were over 100,000 ohms, and the worst one was 668,000 ohms, which is about 2/3 of a megohm. Just way out of tolerance. If you look at a cross section of the plugs, and on the left we have a Champion, on the right we have a Tempest, you can see that the resistor design is very different. The Tempest plug has a resistor that is fired in during the manufacture. It's integrally sealed into the plug, whereas the Champion resistors are screwed in, and they're actually easily removable. If you look into the contact well of a Champion plug, you'll see that the contact has a screwdriver slot in it, because the contact screw is actually a screw. And if you unscrew it, you'll discover that there's a spring and a little resistor chip in the plug. Whereas if you look in the contact well of a Tempest plug, you don't see a screwdriver slot, because the contact is not a screw. It's integrally fired in when the plug is manufactured, and it's permanently sealed. The fact that the Champion resistor is not sealed apparently is the cause of the problem. Here's another cutaway view where you can see the difference in construction, and the fact that the resistor in a Champion plug is secured with a contact screw and a spring, whereas the resistor in a Tempest plug is fired in. And here's a Champion plug where actually the contact screw has been unscrewed, and out popped the spring and the resistor. Now we originally thought that the problem with high resistance was that the spring was getting weak and wasn't making good contact with the resistor. Of course, there's no spring in a Tempest plug, but it turns out that in fact the problem appears to be with the resistor itself. Here's a case where two little resistor chips were removed from Champion spark plugs and measured directly, not inside the plug, but measured separately. And you can see one of them measured 15,000 ohms, the other measured 5 megohms. They're supposed to measure somewhere between 1 and 2,000 ohms. So clearly the resistor itself is the thing that's going bad. And as we talked about, high resistance is a real problem, because as the resistance gets higher, the spark starts to get weak, so you can get hard starting, you can get rough running, other symptoms of poor ignition performance. But if the resistance gets high enough, where it's getting into the 100,000 ohm range, then you can start getting real collateral damage. You can get arc over or flash over inside of the contact well of the plug, which destroys the insulation of the silicone cigarettes that are at the end of the spark plug leads. This is particularly a problem if you don't have all-weather plugs. You can get magneto flashover and damage the magneto itself, and that's particularly a problem if you're using slick mags that have small spacing in the distributor. And you can have damage to the ignition harness, where the spark actually goes right through the harness ignition, the harness insulation, as opposed to jumping the spark plug gap, simply because the plug resistance is way high. The standard bomb test that is normally used when plugs are being reconditioned typically will not detect high resistance. The plug will look fine in the bomb tester. And so the ohmmeter check, which is not standard procedure, certainly for most mechanics, and not documented in the Champion service documentation, the ohmmeter test is really essential to keep track of this. This seems to be a problem with all Champion plugs, both the fine wire kind and the massive electrode kind. And as I indicated, we've never seen the problem happen with Tempest plugs, and that's not surprising because of the fundamentally different design of the Tempest plug when it comes to the resistor. Tempest has actually come out with a spark plug resistance tester. It's about $125. But unless you're checking a huge number of plugs, there's really no reason you need something like that. Checking it with a regular ohmmeter works dandy. Let me talk to you about a second problem that we've been seeing with increasing frequency in the last couple of years, and that is cracks of nose core insulators. These cracks mostly seem to be confined to Champion fine wire S-series plugs. We very seldom see cracked nose core insulators in the massive electrode plugs, and we have never seen one in fine wire Tempest plug, although to be honest with you, we don't have enough experience, enough service history with Tempest fine wire plugs to really have drawn any conclusions. But again, the Tempest fine wire nose core insulator is a very different design than the one Champion uses. It's much beefier, but we've been seeing these insulators come apart in these very expensive Champion fine wire plugs very, very frequently. You may have noticed that in that spark plug tray I showed you earlier that had all of the markings on it, 3 out of the 12 plugs, and those were all Champion fine wires, had cracked nose core insulators. Of course, the cracked nose core insulator can cause ignition problems, but it also, because the cracked portion separates itself from the plug, it can start getting very, very hot and cause destructive pre-ignition. And we have seen several instances where we believe that cracked nose core insulators actually destroyed a cylinder and melted a piston. So this can be pretty serious. Now, Champion has written extensively on this topic, defensively, by the way, but they are convinced that the cause of these cracked insulators is that people are running more and more Lena peak. And it's not the Lena peak operation that causes it. It's the transition between Richa peak and Lena peak, or vice versa, where you're passing through a mixture where light detonation is likely. And I think Champion's probably right in their analysis. Now the fact is that more and more people operate Lena peak. I've been operating Lena peak for 15 years. I'm not about to change. So, I would be the last person in the world to suggest you shouldn't run Lena peak in order to protect these Champion fine wire plugs. What I would recommend is if you run Lena peak, don't use Champion fine wire plugs because they're obviously vulnerable. Now, I think a big part of the problem is, and I'm not going to spend any real time on this because it's covered in my leaning webinar, but I think part of the problem is that a lot of people who do run Lena peak do the transition from Richa peak to Lena peak wrong. If you watch me fly my airplane, when I level out and cruise and want to transition from a Richa peak climb setting to a Lena peak cruise setting, I yank the mixture control back quite aggressively, and I only spend maybe 2 seconds in the process of going from Richa peak to Lena peak. I see a lot of pilots who do that leaning by reference to EGT, which means they go very, very slowly through this bad area, what George Brawley and company call the red box, where you don't want to be. And you have to go through the red box to get from Richa peak to Lena peak, but you don't have to spend a lot of time there. And I think part of the problem is that pilots do this slowly because they're trying to lean with reference to EGT, something I never do myself. And so they dwell in this red box area and set up light detonation, which really doesn't hurt anything except apparently Champion fine wire spark plugs that have these fairly fragile nose core insulators. So again, if you operate Lena peak, first of all, I would not spend a lot of time transitioning from Richa peak to Lena peak or vice versa. You should do that swiftly. But second of all, you may want to consider avoiding Champion fine wire spark plugs if you run Lena peak because they seem to be vulnerable here. So just to summarize a few recommendations, and I'll open up for questions. If you use Champion spark plugs, whatever kind of spark plugs, do check the resistance with an ohmmeter every 100 hours. Every time the spark plugs are out for cleaning and gapping, put an ohmmeter on them, check the resistance, and if the plug measures more than about 5,000 ohms or so, throw it away and replace it. If you operate Lena peak, you may want to consider avoiding the Champion fine wire spark plugs, the S-type spark plugs, because they have shown a vulnerability to nose core insulator cracking, which we think, and Champion thinks, is related to the transition between Richard Peak and Lena Peak, going through the red box, if you will. Finally, I've been using Tempest plugs and their predecessor, the Autolite, the Unison Autolite plugs, for the last 10 years. I've always been very happy with them. I personally think they're a better designed plug, and I use nothing but Tempest plugs in my airplane. Have done so for years. Or Tempest or Autolite, as I said, they're basically the same. They just Tempest bought the Autolite line from Unison when Unison decided they want to get out of the business. And for our managed maintenance, or 400 or so managed aircraft that my company manages, we recommend that that our owners use Tempest plugs just to avoid some of these issues. At any rate, with that, let me open things up for Q&A, Tim. And while we're doing this, I will leave my contact information up on the screen. If any of you have questions that Tim doesn't have time to go through tonight, or think of something later, or have a very specific question specific to your particular airplane that you think would be best handled offline, please feel free to send me the question in the email, and I always answer every single email. In any case, Tim, take it away.
Great presentation, Mike. Thank you very much. Very interesting and informative as always. We do have a number of questions here, and let me start in with them. Robert asks, fine wire versus massive, which is better?
Well, you know, there's no clear-cut answer as to which is better. The fine wire plugs cost 3 to 4 times as much and last 3 to 4 times as long. So on a life cycle basis, if you measure the cost of the spark plugs by the hour, it's pretty much a push, provided that the fine wire plug actually lasts for its full life, which ought to be something like 1,500 hours, the better part of a TBO. The bad thing about fine wire plugs is that if you get a cracked insulator, or somebody drops the plug, or somebody breaks off the little iridium electrode when trying to adjust the gap, all of which things are not hard to do, you've just lost a $100 plug. The main advantage of fine wire plugs is their resistance to lead fouling. So if you have a lot of problems with lead fouling, you may want to consider using the plugs. If you're not having a lot of problems with fouling, using conventional massive electrode plugs, then there may not be any particular compelling reason to go for the high-priced plugs. Again, we are seeing this nose core insulator cracking problem with the Champion fine wires for engines that are operated Lena Peak. I think part of that is due to the fact that the Champion fine wires just have very fragile nose core insulators, and part of the problem is that a lot of pilots who operate Lena Peak don't do the transition quickly, do it slowly and agonizingly, and watching their EGT gauges, and aggravate the detonation problem that causes the cracking. But in any case, if you do operate Lena Peak, again, you might want to either avoid fine wire plugs, or if you want to use the fine wire plugs, use the Tempest ones, which seem to be a little bit more physically robust. That's, I guess, all I can really say about the trade-off between the two kinds.
Great. Okay, thank you. Gary asks, I have a JPI engine monitor with CHT spark plug sensors. Any tips regarding these thermocouples, torquing or cleaning?
Yeah, I'm not crazy about the using spark plug gasket type thermocouple probes, to be honest with you. They read higher than normal probes. Typically, a spark plug gasket probe will read somewhere on the order of 40 degrees Fahrenheit higher than if you were using a conventional probe that screws into the boss at the bottom of the cylinders. Now, there are some engines that don't have a CHT boss, where you don't have any choice but to use those gaskets. But if you can avoid using them, I would suggest using a conventional probe. When you use a spark plug gasket probe, of course, you can't replace the spark plug gasket each time you change the plug. You're stuck with that thing, and it doesn't seal quite as well, and so on. But as far as I know, the torque spec is exactly the same. Again, you would torque the plug to 25 to 30 foot-pounds for a Continental, or 30 to 35 for a Lycoming. Whether you're using a normal annealed spark plug gasket, or whether you're using one of these CHT, a gasket type CHT probe. And I'm not sure if I answered the question, but that's all I can think of to say on this subject.
Great, good answer. Okay, Sean asks that, he says you mentioned the 37BY for small Lycomings. I have found that it works excellent in my 0360 F6A1 in my 180 horsepower Lycoming. Would you recommend something else to avoid fouling?
Well, the only thing that, and unfortunately I don't have my spark plug reference book open in front of me, but I'm not sure if that REM37BY is approved for the engine. If it's approved for the engine, I see absolutely no reason not to use it. I was under the impression, but I could be wrong, that the REM37BY was primarily used in the little Lycoming 0235s. But if it is approved for that 360 engine, then I see absolutely no reason not to use it. I would just have to look it up in the book, and I don't have it in front of me right now to verify whether it's approved. If you don't have that information handy, drop me an email. I'll look it up for you.
Great. Paul asks, in general, are hot plugs having a shorter reach over cold plugs?
No. The heat range is not a function of reach. It's a function of core nose insulator length, and that's actually independent of reach. You can't associate the reach of a plug and its heat range. Those are two independent parameters.
Okay. William asks, are any plugs reclaimed when retired?
Well,
so
I'm
what
not
he's saying is, are they recycled? Is an old plug somehow reworked to be made good again?
There's no way to restore electrode thickness to a spark plug. There's no way. There's no overhauling of spark plugs, if you will. Once the wear has reached the limit value, or something else has damaged the plug, like say a cracked insulator, the plug is discarded. It can't be restored. We obviously recondition plugs every 100 hours, and by recondition we're talking about cleaning and gapping and so on. But no, there's no way. Once a plug is worn out, it is not recycled. There's no way to bring it back. There used to be some old spark plugs back, World War II vintage spark plugs, where you could actually take them apart and change the electrodes and stuff. They have made plugs like that for years and years. Our modern plugs are basically disposable. You throw them out when they get worn out.
Okay, great. Terry asks, my 165 horsepower Franklin engine uses REJ-38 plugs with the single automotive type electrode. What measurements do you use to determine when they need replacing?
Boy, that one is that's interesting, because I've never dealt with those. I've actually seen in the books that some of the old Franklin engines use that plug, but I don't. I really don't have any experience with it. My guess is that you still look at the ground electrode, and when it's become half its original thickness, it's time to reject it. But I'm winging it here. I would really want to look it up. That one I just don't know the answer to.
Okay, fair enough. Jerry asks, some people anneal the plug washers and reuse them. What are your thoughts?
My thought is that for 10 cents, it's not worth doing. You can restore the softness of the gasket by annealing it, but you can't restore its original dimension. It's gotten thinner under torque, and it's not going to spring back when you anneal it. For 10 cents a gasket, which at least is my vague recollection of what these stupid things cost, I think you just throw them out and use new ones. It just doesn't make sense to go to the effort to save 10 cents.
Okay. Joe asks, can you bead blast to clean plugs?
There's a particular cleaning agent that they use. It's it's called sandblasting, but it's not really sand. It's some sort of abrasive material that that's specified by the spark plug manufacturers, and that you buy. It has a Champion or a Tempest part number on it. You wouldn't want to use plastic beads because they would embed themselves into the area between the plug barrel and the core nose insulator, and you couldn't get them back out again. So it would not be good to use plastic beads to blast them with. There's a very specific abrasive that you're supposed to use.
Okay, great. And Dan says he was told by an AMP once that...
I love questions that start like that.
Yeah, that his 0320 uses the same polarity for all plugs. But another AMP told him otherwise. Which is correct?
Well, that's interesting. If it is a 4-cylinder engine, and if it uses the Bendix dual mag, in other words, if it's a O360 or IO360 and it has a D suffix at the end, I believe that the Bendix dual mag does fire alternating polarities, unlike a conventional mag. I would not stake my life on it. I would want to go back and look it up, but what he was told by the first A&P may be correct if he has an engine with the dual mag. It would have a D suffix at the end of the engine model number.
And that's what he's got. He says it's an 0320 H2AD.
Aha! The H2AD. So it's I think it's probably out of a Cessna 172N or something like that. Yeah, I think that's probably correct. I think with the dual mag, it's a little different than it is with conventional 4-cylinder mags.
Okay, great. David asks, he has an engine that has an experimental electronic ignition firing the top plugs and a standard slick mag firing the bottom plugs. How should he rotate these bottom plugs, since he can't move them to the top?
I'm not sure I understand the question. Are the bottom plugs different?
Well, I assume that that's what he's saying because they're electronic.
Yeah, I mean, I'm not familiar with the. I thought even when you used electronic ignition as one of the mags, you were using the same plugs, but I might be wrong. I guess I don't have enough information to answer the question.
Right.
Also, with the electronic ignition, I'm not sure whether that one polarity issue is even relevant, because a lot of the electronic ignitions use a wasted spark thing where they fire the plugs in alternate polarities. But I just don't have enough information to answer the question.
All right. Floyd asked, what was the main plug condition that resulted in hard starting?
Well, there are a couple of things that can result in hard starting. Letting the gap get excessively large and not bringing it back to something close to 016 will cause hard starting. a champion plug where the resistance value has gotten high will cause hard starting, and plugs that have excessive deposits on them because they haven't been cleaned recently will cause hard starting. Any of those three things can do it.
Okay, great. And Ron says, if the gap is accidentally closed to, say, 15 thousandths, why not carefully open the gap?
Because you can't.
Specified?
I'm assuming we're talking about a massive electrode plug. You can't open the gap. Now, look, to be honest with you, if the gap was 15 instead of 16, I'd put the plug right back in service. That's a self-correcting problem in a very short period of time. But if the gap were much smaller than that, I would toss the plug. And the only way that happens again is if you get a little ham-fisted when you're adjusting the gap, and after you've ruined a plug or two, you get some pretty good feedback, and you don't do it anymore.
Great. Okay, Vincent asks, or he gives a note, I guess. He's making a comment here. He says that cranking the engine with the lead off of the plug will cause the high resistance situation also. So
That's
I would
true.
I would say never turn mags on and crank engine with leads off the plug.
I think that's a very good thing. We will once in a while do it with one lead off of one plug just to do a field verification as whether the mag is firing or not. But we'll only do that when we're turning the mag by hand and snapping the impulse coupling through one turn or something like that. We certainly would never crank the engine with a starter or anything with the ignition leads disconnected, and for exactly the reason that he said. That's correct. That's very good advice.
Okay. And Nick is asking, does aircraft spark plug service that you mentioned earlier measure spark plug resistance as part of their service?
They don't. Again, they are an FAA repair station. They are obligated to follow the manufacturer's guidance, and the Champion guidance doesn't say anything about measuring resistance. And I've actually talked to Jeannie about it down there, but they do not measure the resistance. It's aircraft spark plug service. So I always just measure it when I'm ready to install the plugs. And again, I use Tempest plugs, have for a long, long time. I've never seen a Tempest plug with a resistor that measured out of spec ever. But I see it all the time with Champion plugs. In fact, I had 5 Champion plugs that I carried in the wing locker of my airplane as spares, and just for the heck of it, I measured them, and 3 out of the 5 were above 5,000, and one of them measured completely open circuit, or at least more than 10 megohms, which is the highest that my ohm meter will measure. 2 of them were in the hundreds of thousands of ohm range, and 2 of them were below 5,000 ohms. So I chucked them.
All right. Yeah, sure. Gary asks, what causes the resistance to increase?
Well, I don't know, but I have to assume that at least in part it's due to the fact that in the Champion design the resistor is not sealed. The compartment that it's in is not sealed. It's just got that little screw on it that doesn't even have an O-ring or anything on it. So I just assume that the resistor is somehow attacked by the elements or something. But I'm just speculating. I don't know that anybody really knows the answer to why it happens. We've been bugging Champion about it for a long time. They don't seem even slightly interested in changing their spark plug design. So we just have to deal with it.
Okay. Peter asks, I run Champion fine wires in my IO 550B A36 Bonanza. I often have black crud build up in the contact well area, and the plugs fail Lena Peak mag checks. I clean them and they are good for another 50 hours or so. Is this combustion products coming in past the ceramic, or is this a Champion quality problem?
Well, that's an interesting question. Even with either of the designs, there should not be any combustion leakage into the contact well area. Both of the plugs have, both of the brands of plugs are supposed to be completely hermetically sealed in that regard. And if there's crud in the contact well area, I would assume that either there is flashover happening, and the crud is actually, carbonized insulation from the cigarette, or possibly moisture is getting in. And I don't know whether the plugs that he's using are the H, the all-weather plugs, or the M, the standard plugs. The all-weather plugs have a much better seal and have a much larger contact well diameter, so the likelihood of flashover is much reduced. Also, once crud gets in there, it obviously the crud is conductive, and so you have to clean the contact well out scrupulously clean. The best way to clean it is with a Q-tip and MEK, and then also use the same sandblasting material that's used to clean the nose side of the plug. But if there's any contamination in the well, that will stimulate flashover once the plug goes back into service. So the contact well needs to be cleaned scrupulously. If by some chance this Bonanza is using M-style standard plugs as opposed to H-style all-weather ones, and this is a persistent problem, it might be worth biting the bullet and changing over to H-style plugs, which would require replacing the ignition harness. But the ignition harnesses aren't horribly expensive. They're $300 or $400 for a complete harness, so it's not an out-of-the-question thing to do if this is a persistent problem.
Okay, great. David asks, the spark plug copper washers have round side and flat side. Any preference as to which side should face the spark plug?
It's very interesting. I have looked and looked to find written guidance somewhere about that, because I always puzzled about that. And if it exists anywhere, I haven't found it yet. My practice is always to put the flat side of the gasket against the plug, as opposed to against the cylinder head. It makes sense to me that way, but to be honest with you, I have not yet found a definitive document that tells me that's the right way to do it. It's just the way I've been doing it for years. I think it's right, but I can't prove it. And I actually, in preparing this webinar, I went through years and years of champion service bulletins and stuff, just kind of looking for things that I wanted to talk about. And in all of this material I went through in preparing this webinar, I did not find one syllable that addressed that issue. So it's very strange.
Oh, okay, yeah, the unanswerable. All right, a couple more questions here. We're just about running up the end of our time for the webinar. I want to get a couple more questions.
How are we doing on the backlog? Are we making much progress?
Yeah, we're making through the questions pretty good here.
Great.
Okay, so
for change.
John, right, yeah. So John asks, what does Mike use as a reference for transition from Richa Peak to Lena Peak?
Well, I don't want to really get into that, because there's a whole leaning webinar on that. But basically, when I transition from Richa Peak to Lena Peak, in my airplane, I typically do it by reference to a fuel flow, because I've been flying the thing so long, I know what fuel flow to lean to. But if I'm flying a strange airplane, I just pull the mixture back fairly briskly until I feel or hear, or both, a slight decrease in power. And once I feel or hear that slight decrease in power, I know I'm on the lean side of the red box. I don't ever use EGT as a leaning reference, because the only way to do that, to use EGT as leaning reference, is to is to lean slowly and watch to see where the EGT peaks, and that's exactly the wrong thing to do because it keeps you in the red box, keeps you where you don't want to be.
Right.
A lot more detail in the leaning webinar, so I would recommend, if you haven't looked at that, you might want to do that.
And all the webinars that EAA has conducted have been recorded and placed on the EAA website, eaa.org/webinars. And there is a recording of the webinar for leaning basics that you did there. So
yeah, I think tonight's webinar is the 17th one that we've done on the server, and we do a new one, of course, the first Wednesday of every month.
Yes, sir. Okay, so Joe asks, how do you tell if a magneto lead is firing negatively or positively?
I don't know. I guess you have to look it up, but I'm not sure why you would worry about it. What's important is simply that the odds on the top and the evens on the bottom fire in one polarity and vice versa. So as long as you move the plugs from positive to negative position, you'll be equalizing the wear. I suppose one way of telling whether it's positive or negative is to leave the plug in the same place for a while and then watch which electrode wears out. But to be honest with you, I can't tell you right offhand which ones are positive, which ones are negative. I just know that the odds on the top and the evens on the bottom are one way and vice versa.
Okay, and we've had a few questions in here on this one, and they're asking, what is the bomb test?
Oh, a bomb tester, I should have explained that because that's kind of a colloquial phrase. But both Champion and Aircraft Tool Service and a couple of those companies make these spark plug testers, and I had pictures of two of them on one of the slides. And the bomb tester is a device where you insert the spark plug, the nose of the spark plug, into a chamber which is pressurized with shop air, and it's pressurized up to trying to remember, it's either 115 or 135 psi depending on which kind of plug you're testing, and then it's got what amounts to an old Ford spark coil that you connect to the plug, and it's got a little viewing window and a little mirror. So you put the spark plug into the nose of the spark plug into this pressurized chamber. You crank up the pressure. It's got a little meter on it and a regulator. And then you start firing the spark plug, and you look through the mirror and view the actual spark. And you can see whether the spark looks healthy or not. And that's basically what is involved in what's called bomb testing the spark plug.
Gotcha. Excellent. Okay, so Boyd asks, it is rumored that Cirrus suggested all fine wire plugs be removed. Is this true?
It's not rumored. It's for sure. The sequence of events was that that first Tornado Alley turbo, which holds the STC for the turbocharged Cirruses, or the turbocharging system on the Cirruses, and also has STCs for turbocharging systems on, or turbonormalizing systems, I should say, on Bonanzas and a couple other kinds of aircraft. After years and years of trying to get Champion to do something about this core nose insulator cracking, finally gave up and issued a service bulletin. It's not an AD, it's a service bulletin, asking that all Champion fine wire plugs be removed from service on their turbonormalized aircraft equipped with a turbonormalizing STC, which included almost all of the turbocharged Cirruses, or the turbonormalized Cirruses. Subsequently, some months later, Cirrus issued its own service bulletin, which covers not only the turbonormalized Cirruses, but the normally aspirated ones as well, and suggested that that the fine wire plugs not be used anymore. So it's not a rumor, it's for sure. But again, it's not an AD, it is a service bulletin. You aren't required to comply with it, but I think it's a real good idea.
Okay, great. And last question here, can you mix fine wire and massive plugs on the same engine.
Absolutely. And in fact, as I think I mentioned earlier, there are some people who are experiencing some fouling problems that run fine wires as their bottom plugs and massives as their top plugs, and there's nothing at all wrong with that.
Great. Well, Mike, we've reached the end here, and I sure want to thank you for sharing all your information with us and all the attendees. Very informative as always. And to all the attendees, thank you so much for attending tonight and tuning in to the EAA webinar. Did you have a little closing comment you wanted to make, Mike?
No, I don't think so. I guess next month the webinar is called to TBO and Beyond. It's a webinar about how to get our engines to last a long time, and it's one that I've given a number of times at AirVenture, and I'll be doing it in webinar form next Wednesday, or not next Wednesday, but first Wednesday of next month of October.
First Wednesday in October, yes, October 3rd. Looking forward to that one. That will be interesting. So,
and I guess we've scheduled out our monthly ones now out till March or something like that. So there's a whole bunch of new webinars coming.
Yes, we got them scheduled till March, and you can see the schedule on the EAA.org/webinars website. So with that, Mike, thank you very much. Attendees, thank you very much, and have a good evening, everyone. Good night.
Yeah, thanks, everybody. Good night.